All right, Gauss's law. We have a closed loop integral of the electric field dotted with some area of element, and it's that closed area. So you're talking about a bubble, you're talking about a cube, some kind of shell that's completely closed. And that is equal to all of the charge that's enclosed in that shell, and here divided by epsilon naught. So because it's an epsilon naught, we're talking about the charge being in vacuum rather than in water or some material like that. Okay, so this is Gauss's law. It talks about the total flux, or the net flux, through this closed area gives you information about the enclosed charge. One way to interpret this is that charge creates electric field. If you have charge, you've automatically got electric field, and we've talked about that in terms of the electric field due to a point charge. Where here K is 1 over 4 pi epsilon naught, which we've seen before. So if you have charge, you have electric field. Let's focus just on Gauss's law itself. Okay. So this closed shell, it does not have to be symmetric with your system. That's just something that we impose to use it. So any completely closed area, so surface area, gives us this information. Now, how we use it in terms of trying to find the electric field, we want to find the electric field, then we use the symmetry. And we do that by looking at the symmetry of our charge distribution, whether it's a point, a line, some kind of spherical shell or a solid sphere, whether it's a conducting material or an insulating material. So we'll do that. And what we want to do is we use the symmetry by, we want to match the Gaussian surface. That's the shell that you are using. It's mathematically defined. It's not an actual shell. So match the Gaussian surface with the charge. With the charge distribution. So as I mentioned before, things like a point charge, line of charge, shell of charge, whether you're talking about spherically symmetric. So that's a type of charge distribution we're looking for. All right. Now, why do you want to use the symmetry and match the Gaussian surface with the charge distribution? The reason that you want to do that is that way the electric field is then constant. If the electric field is constant, then what we can do is we can pull it out of that integral. Okay. So the electric field is constant. You can pull the electric field out of the integral, and let me go over to this other part of the board. So if E is constant, okay, then what happens, you're able to pull it out of the integral, and so you have the electric field, and what you're doing is you're adding up all the little bits of that surface area around your shell, and so this is just surface area. Of some closed surface, because then you get some electric field is equal to the net charge that's enclosed in that Gaussian surface over epsilon naught times surface area. Okay. Going to the exam problem, what we have is a hollow metal sphere that has inner radius little a and outer radius little b. So we draw this up here. From the very center, my inner radius of A and my outer radius of B. It's a conductor, and so all of this area right in here, is some kind of metal. And that's going to come into play when we start applying Gauss's law to this problem. Okay, so for this shell, the problem says that we have a charge on this shell of positive 2q. Okay. And at the very center of the shell, we have a point charge. I'm going to draw it like that so you can see it better on the video. And that point charge has just a charge of q. Okay. And then for the point charge, we have positive q. The problem wants you to find out what is the electric field outside, in between A and B, and in the center. So mathematically, when the distance is larger than B, between A and B, oops, there we go, and inside A. So the symmetry tells us we want to use a spherical Gaussian surface in Gauss's law, and because the electric field points radially outward, we just get the magnitudes. So E, dA. So there we go. So we're going to be using that. We can use it in all three regions of this problem. And we know that that's Q enclosed over epsilon naught. So this tells us the magnitude of our electric field. So let's start outside of this metal sphere. So here's my Gaussian surface. I'm going to indicate that with the dashed line. Okay. So R is greater than B. All right. So in this case, what's my total enclosed charge? Well, I've got positive 2q from the shell. I have a positive q point charge sitting at the center. And so my charge that's enclosed is positive 3q. We still get epsilon naught. Okay. Now, because of the electric field lines pointing radially outward, because we have this spherical Gaussian surface, and it's all centered on the center of this system, we can pull the electric field out of that integral. So E is a constant all along that Gaussian surface. So pulling it outside. Now, all I need to do is, what's the surface area of my Gaussian surface? Remember that this is a cross-section. So, what's the surface area of a sphere? I've got E, times 4 pi r squared. And I'm using the radius of my Gaussian surface. Okay, my marker's drying out a bit. And so that equals, from here, positive 3q over epsilon naught. Now I just need to solve for the electric field. And I get positive 3q over 4 pi epsilon naught r squared. That's the magnitude of my electric field. So when you're outside a spherical distribution of charge, the electric field acts as though it's all due to that charge right at the center. And so this, remember, is outside of the metal shell with that point charge. Check. All right, I'm going to jump down to, what about if we're completely inside the sphere? Just because we're moving on, I'm going to erase my original Gaussian surface for here. Now, what about if I'm in here? In this case, we're still using this spherical symmetry. I get to pull the electric field out. I already know the surface area of a sphere, and I know what the net charge is inside this little sphere. Okay, so pull the electric field out of the integral. Now, remember, I'm specifying that little r is less than little a. Okay. So that's the result of the integral part. What's my my enclosed charge? It's just positive q over epsilon naught. So the electric field is equal to positive q over 4 pi epsilon naught times r squared. just like we have for before, except that the charge is different. Hopefully this isn't surprising, because hopefully you remember that this is what the electric field is for a point charge. Check. All right. Now what we get to do is apply Gauss's law and our understanding of conductors between A and B. On the test or on homework, I wouldn't expect you to erase these parts. Okay. I still want to match the symmetry, so it's spherically symmetric. When we were talking about the radius being larger than B or smaller than A, we started off with, well, what's the enclosed charge? Now we have to remember a characteristic of conductors. We are inside, in the material of a conductor in electrostatic equilibrium. We automatically know that the electric field is 0 in that region. And so that means that our integral automatically is equal to 0. So if I have 0 is equal to Q enclosed over epsilon naught, well, how does that work? I know that I have positive Q here. I know that in conductors, charge only exists on the surface. And so that means that there's negative Q distributed evenly around this inner surface. Okay. And so, just all along here. So we have this negative Q distributed over the inner surface of the hollow metal shell. That cancels the positive Q at the center, okay? And so therefore, that's how you get 0 electric field inside the metal. Now, we think about like opposite charges attract, like charges repel. Well, of course, this positive charge at the center is going to attract the valence electrons, that sea of electrons in the conductor, until it's all balanced out. Okay. But now let's talk about charge conservation just for the shell itself. We know that the shell has a charge just by itself of positive 2Q. The only way, we're not adding charge, we're not taking charge away, it's just charge is being redistributed. So, if we have negative Q distributed along the inner surface, and excess charge is only on the surface of conductors, then what happens, use this one, is that we end up having positive 3Q distributed on the outer surface. So all around here, positive 3Q. What is the net charge? It's maintained. Positive 3Q minus Q gives me plus 2Q. E field. For R greater than B, you had that the E field was equal to plus 3Q over 4 pi epsilon naught R squared. For in between, you have that the electric field is equal to 0. And for inside, what you ended up having was that the electric field, the magnitude of the electric field, is equal to plus Q over 4 pi epsilon naught R squared. So, recapping, that's the electric field for these 3 regions for the system. Okay. Now, I drew the solid lines around the outer surface and the inner surface of this shell, just to help get the point across that the excess charge is distributed evenly around this surface. Okay. But when we typically draw sketches, and part of the exam question was draw an informative sketch of the system, for charges we typically just draw pluses and minuses. So, yes, this would have worked, but it's not necessarily the conventional way that we draw these sketches.